Hello everyone. We are going to go through the solution of problem 3-24A. So hopefully it could help you to solve the other similar examples. So here we have the cantilever beam and a distributed load here of W. So the cantilever beams are the beams which are fixed from one side and they are free from the other side. So if we want to remove the wall or the fixed plate here, we need to replace the effect of that fixed constraint or the wall by having one reaction force and one moment here. The F, this force here, the capital F here, is the concentrated load. So the F and W, both of them are external loads, and R1 and M1 are internal loads or reaction forces. A and L are lengths. We have all of these informations here. L, A, W, and F. And what we want to do, we want to find the reactions, the maximum shear and the maximum moment. So if we use the singularity method and the function, the first step is to write the singularity function for the load or load function equation. So Qx. The first load is the reaction moment, M1. So here we have a minus M1, Y minus because is counterclockwise. You could use the clockwise here, it doesn't matter, and use the M1. The final solution will correct us and will give us the right direction. So minus M1 bracket X minus 0, Y 0, because the moment is located at 0 to the power of minus 2. Y minus 2, because based on the policy for writing the singularity functions, the power for the concentrated moment should be minus 2. Then we have the concentrated force R1 located at 0, so it will be X minus 0 to the power of minus 1. Y minus 1, again, because based on the policy we had for the singularity function, for the concentrated load or force, the power is minus 1. Then we have minus W, Y minus, because the direction of the load is downward. X minus A, because it starts at the A location to the power of 0 for contributed force. We have power 0. And again, we have another concentrated force, minus F, multiplied by X minus L to the power of 1. So now that we managed to write a proper load function, the next step is to get the integral to find the shear function Vx. So we'll get the integral, the first one. Again, it doesn't follow the regular integral method for singularity function. So x to the power of minus 2, the integral of that will be x to the power of minus 1. We'll get the next one, the next term here, the integral will be r1 x minus 0 to the power of 0. The regular integral is different. I encourage you to check the books and see how you should get the regular integral of x to the power of minus 1. The next term will be minus w x minus a to the power of 1. And the next one will be minus f x minus l to the power of 0. When the power is 1 and above, the integral will be similar to the regular integral. Integral of singularity functions will be similar to the regular functions. Now we have v. We need to get a second integral to find m function. You see that this one is easy because the power is minus 1. We just need to increase the power. This one is 0. We need to just increase the power. This one is like a regular function. And the integral of this term will be minus w x minus a to the power of 2 divided by 2. This one, we just need to increase the power of integral by 1. Okay, now that we have a shear and the moment function, the next step is to find the reaction forces. We have two reaction load. One is force, the other is moment. So we have two unknowns. We need two boundary conditions. And the most simple boundary condition is that at the XL plus, both the shear and the moment will be 0. Why is that? Because if you select a small or infinitesimal element at the end of the beam, there is nothing that could hold that infinitesimal element, and the shear and the moment will be 0. That discussion is already covered during the lectures, but for a cantilever beam, this is one of the best conditions could be used. Now, if you substitute these conditions into the equations that already we derived, we'll have the first and the second equations. Now we could find R1 and M1 based on these two equations. Now if you substitute the value of F, A, L, and W, you could find R1 and M1. Okay, now is basically the time to plot them. You could use any software. Here in the solution of the book, they use MathSCAD, but you don't have access to that, so you could use MATLAB for the whole length of the beam, which is from 0 to L. You could just substitute the value of the X and find V and M and plot that. Now we have the plot for the shear and the moment. Okay, and you basically could see where is the maximum moment and where is the maximum shear. From the graphical method, you know that you could find the diagram of the moment by getting integral of the shear diagram. And you see that from here, 0 to A, the shear force was constant, is equal to the F1. And then we have this gradual drop on the shear. For the moment, so the area under the curve here increases. So we have this line here. So you know that the integral of a constant is a line or a linear function. So it will be a line. And then here we have a line. So from that point, we'll have a parabola. So the curve is basically very small, so you cannot see the curve much, but you should know that this is a different function on this area than the this area from 0 to a. What you could do, you could find the maximum based on the plot, and the Vmax is from 0 to a or at 0, and the Mmax also based on the plot will be at 0. So now you have Vmax and Mmax. Why do we care about the maximum shear and moment? Because later, when we want to find the critical point, to do the analysis of stress and find the maximum stress on the beam, we need this cross section. So the critical cross section of the cantilever beam here is obviously the base. At the base, we have both the maximum shear and the moment. And at that cross section, for sure, we will have the maximum stress. When we have a maximum stress, then at that point, we will have the lower safety factor, and the safety factor always should be more than 1. So this is the main reason we do the beam analysis, and we are basically concerned on the cross section with the maximum shear and specifically moment.